Alright, so this lesson is 4.7 part 1, and we're going to discuss the law of sines and the law of cosines, but the real basic version of it. So I believe you had minimal exposure to the law of sines and cosines in Honors Algebra 2, and then if you took our trig course, you had more exposure to it. So we're going to be solving for non-right triangles, oblique triangles, and my mouse working here, you're going to remember some things from geometry about the clues that you're given regarding the triangle. So we're going to have situations where you have the angle side, the angle side angle, later on the side for law of cosines, and then the one that in geometry they wouldn't let you use for congruence postulates, the side angle, or in geometry all the little sophomores started giggling when they write that down. And then your geometry teacher said, please don't say that word, so then they started calling it SSA. The idea was you couldn't prove triangles congruent through SSA, and we're going to learn more about that why today. And the issue is, when you have side angle, there are cases called the ambiguous case where that actually can produce two different triangles. Also, it has the case of possibly not producing any triangle, like the triangle wouldn't close. So we'll learn more about that later on in the lesson, but this is the proportion for law of sines. And remember, you can reverse the proportion so the leg is over the sine of the angle. It doesn't really matter, you just got to stay consistent. I always do sine of A over A, that order, so if you want to stick with me, and use that order as well. Remember, in geometry, trig, PreCalc, capital letters on the vertices of a triangle are the angles, and then across from said angles, they usually label the sides, the legs, with the same letter, just lowercase. So that's easy for us to notate on the picture if they give us just words in a problem. Now, if you have an application question, instead of calling things A, B, and C, it might help if you call them like what they really are. For instance, if you're trying to find the distance between two cities or something, call the vertices some abbreviation of the city. So, first, we're going to stick with law of sines, and then we're going to talk about law of cosines. And you have to be able to use both because it depends on the case that you're given. So if we have angle side angle, or side angle, we have to use law of sines. So we have to make, I know we've been flipping between modes for this class, but we're going back to degree mode because of the nature of the problem. And we are going to start with this example here, where we have angle A, angle B, and then we have side A. So the first thing I'm going to find is actually just an old geometry question. Triangles add up to 180 degrees. This is 130. So angle C here has to be 50 degrees. So I'm going to notate that somewhere on my paper. That's the first thing we had to find. Now we can set up law of sines. And turns out we're going to have to set up law of sines twice because I have two more unknown legs. So I always tell my kids to start with the part of the triangle that you know everything about. So if I look at my triangle, I know side A and angle A. So that's going to be the beginning of my proportion. Sine of 30 over 15 equals, and we're going to have to set up two proportions, so I'm going to go ahead and start the other one as well. So it doesn't matter which one you set up next, because we're going to have to set up one. So, going alphabetically then, sine of B, which is 100, over leg B, and then same thing for C. Sine of, we just found that to be 50, so sine of 50 over C. So this first proportion, I'm going to show you the longhand algebraic, set up the equation cross multiply business. And then from then on, I'm just going to show you how I shorthand those steps on my paper. And even to this day, I still have to write down the steps shorthanded because I type things backwards because of my dyslexia, so I have to write something down. All right, so when I solve the proportion, don't we cross multiply? So 15 times the sine of 100. That might help you to remember that there's going to be parentheses on your calculator. Equals B times the sine of 30. And then remember, if we're going to solve for B algebraically, one more step, I'm going to divide by the sine of 30. And all of this is going to happen in one step on your calculator once you remember the steps. So on my calculator, and for the sake of time, because I already recorded this lesson and then my computer crashed and now I have to record it again, so I'm running short on time here. I'm not going to show you on my computer calculator how to type this, so please practice, pause the video if you need to, but get in degree mode, type 15 times the sine of 100, make sure you close the function, and then divide by the sine of 30. It doesn't really matter if you close that function, but it's a good habit. And after typing that, you find out that leg B is 29.5. There's no units on this problem, so I'll just leave it as 29.5. Same thing here. For finding leg C, we're going to do the same algebraic math. We're going to multiply this diagonal. So this is how I shorthand my notes. I multiply this, and then off to the side of this other thing, this sine of 30, I'm going to divide by that at the end. So I'm going to type 15 times sine of 50. Make sure you close your parenthesis, and then divide by sine of 30. And I got C to be 23. Lovely. All right. Let's do one more of these real basic law of sines graphs, and then we'll talk about the fun ambiguous case. So for number 1 here, 170 degrees so far, so that would leave angle B to be 10 degrees. Oops, that's not what I meant to write. Angle B is 10 degrees. When you have a triangle, you should be finding all 6 things. So since we already had 3, we're supposed to be finding 3 more things. And this original angle, that geometry problem, is the first thing. All right, I didn't label our triangle at all here. So across from angle C is side C, across from angle B is side B. So setting up law of sines, we're going to start with the part of the triangle that's all filled out, and it looks like it's A again. So let me use black ink. Sine of 150, oops, over 200 equals, and we're going to have to set up 2 proportions, so might as well get that out of the way. So if I go alphabetically, I'll go B first. Sine of 10 over B, and then sine of 20 over C. Alrighty, so on my calculator now, we're going to type 200 times the sine of 10, but I write that on my paper. Make sure you close your parenthesis before you divide by the sine of 150. And you get, let's see, B is 69.5 units, whatever they are. Same math over here, 200 times the sine of 20. Make sure that you close your parenthesis after the 20 before you divide by the sine of 150. And I'm finding leg C to be 136.8, whatever units. All right, so we found 1, 2, 3 things. We have solved the triangle. All right, so that type of law of sines is, I don't want to call it boring, but a little boring. Let's talk about the other case here. If you have the side, and then a non-included angle. What can happen is, with the given clues, you might have a case where this happens, where no matter what you do, the ends of the triangle aren't going to match up. So if this ends up happening, we would say, after our math, we would say the triangle does not exist. Sometimes it does produce a triangle, and then sometimes this happens. And this is why we couldn't prove 2 triangles congruent through angle side-side or side-side angle, because sometimes, besides the fact that they might not even be a triangle, it can produce 2 different triangles. This leg here can swing because the angle isn't locked, and sometimes it produces this triangle or this triangle, depending on what's happening. So that's the word ambiguous coming up in the ambiguous case. It's unclear which triangle they're going to create, therefore I can't prove 2 triangles congruent because I don't know which triangle they're talking about. So in law of sines, and if you look in your textbook, they have all these neat little tests that tell you whether you have no triangles, 1 triangle, or 2 triangles. And I never use those tests because that would require me to memorize them, and I don't want to. So I just find that if I jump into law of sines and I determine whether I have a triangle or not, and if I do have a triangle, do I have a second triangle? Like, that's just as effective as using those tests in your textbook. No offense to your textbook, because, you know, it's totally a way to do it. I don't have enough memory space, guys. All right, so here's what's going to happen. We're going to do law of sines and figure out if we even have a triangle. And if we do have a triangle, what we're going to do is you're going to take the inverse sine of, some number after a little bit of work, and you're going to come up with this guy. And this is our first possible angle. But what we're going to find out in a moment is sometimes, if you have the ambiguous case, you might have a second case where you take the supplement of whatever this dude is, and this gives you our second possible angle. And I'm referring to the same angle. So like maybe we're solving for angle C, and I find out that angle C is 14 degrees, and then I find out, that's kind of weird, it would be 14. Let's say like it's 82 degrees, and then I would find out that the supplement to that, so 98, is my other possible angle C. So we're going to have to set up, in some cases, 2 different triangles and solve them separately. So is it twice the work sometimes? Yes, it is. All right, so remember you can reverse the law of sines proportion if you like that way better. I don't really care. This is a nice diagram of like what it physically looks like when you have a triangle that does not exist versus just a regular old triangle versus the ambiguous case of two different triangles showing up. This is a nice connection to our graph of the sine function. So if you think about a triangle being between 0 and 180 degrees, and I give you a value like, I'm just going to make this up, like 0.71. Make that up. There are two places where your sine function hits a value of 0.71 between 0 and 180. So maybe through your calculator it will find like this angle. I'm not sure which one it finds first. I'll have to think about that. But then we have to understand that his supplement is also an option. 180 minus that. So, nice connection to something we already knew about. All right, yada yada. Oh, your inverse sine will never give you two possible angles. Remember, arc sine is defined between negative pi over 2 and pi over 2. So we just have to remember that our calculator has its limitations, and this is one of them, right? So here, we have, is this on our notes? It's not on our notes. I'm going to skip over this one for the sake of time. Let's go straight to our notes. On the back of our notes here, 3A, they don't even give me a triangle. And you know there's no chance of me drawing a nice triangle, so I'm just going to draw a triangle, ABC. And angle A I don't know, but side A is 12, side B is 8, and then angle B is 61 degrees. So we definitely have the side-side angle set up. I'm still going to set up law of sines. It's possible that I don't know what's going to happen yet, and that's okay. So a sine of 61 over 8. That's the part of the triangle that's all filled out. And there's only one other clue I know, which is A. So we're going to set up the sine of angle A equals 12. So on my calculator, we are still going to multiply sine of 61 times 12, the diagonal that's all filled out here. And then remember, I need you to close the parenthesis there after the 61. And then you're going to divide by 8. Now when you type that in your calculator, so 12 times the sine of 61 divided by 8, you get 1.311 roughly. But we still have the sine of A. So to undo the sine function, because think about what we have here, we have sine of A equals 1.311. I'd have to apply the arc sine, inverse sine. And then I'm not really going to have to do any more work here, guys, because if I tried to apply arc sine to something greater than 1, my calculator is going to come back with an undefined answer, because remember, arc sine is not defined after 1. So you're not going to be able to find an angle that produces a sine value of 1.311, which means to me that this triangle does not exist. All right. So that's the nice part of the possible ambiguous case, is that you might have to do less work simply because you don't even have a triangle. Awesome. All right, so for a little bit of a spoiler alert, turns out we're going to have two different cases on this one, and you will go through this with me and you'll see that it's not really tons of extra work. So this is why I claim it's not worth us using that testing thing to figure out if we have the ambiguous case or not. All right, angle A is 38 degrees, A is 8, and B is 10. So again, side-side angle. Let's set up law of sines. So the sine of 38 over 8 equals the sine of B, which is the only thing I can find right now, over 10. So on my calculator, I'm going to multiply sine of 38 times 10. Make sure that you close the parenthesis on the 38, and then you're going to divide by 8. I don't know what that comes out to on my calculator, but there's still one more step. I need you to hit enter, and you multiply these together and divide by 8. And then we still have to undo the sine function. So at the very end, you're going to inverse sine your answer that you just got. So after typing all that in my calculator, I find out that angle B is 50.3 degrees. So if I fill that out on my picture here, is that what I found? Yeah, 50.3. All right, 50.3 degrees. I fill that out over here. Let's continue on with law of sines. So, finding angle C, I could set up another law of sines proportion. So I'm going to start the same way. Sine of 38 over 8 equals sine... Oh, for Pete's sake, I don't need pre-calc to find angle C. That's just a nice geometry problem. 180 minus 50.3 minus 38 is 91.7 degrees. Hello, Abruzzo. There we go. So now I can finish my law of sines proportion. That says sine of 91.7 degrees. Whoops, I don't need a degree symbol on here. Let's assume it's degrees. Over C. And this is one of those easier law of sines problems where you just multiply and divide. So multiply 8 times sine of 91.7, close parenthesis, and then divide by sine of 38. And after doing that math, I found out that leg C was 13. And that's great, but turns out there's a possibility of a second triangle. So after doing law of sines the first time, I go back to the possibility that B might be something else. Angle B could be the supplement to what we just found in the original case, which is 129.7, yeah. Now I'm going to write that down, and then here's what I have to do. I have to make sure that this still makes a triangle. So 38, 129.7, that's like roughly 160, so I still have room for another angle. So after doing a little geometry question here, 180 minus these two guys, I get 12.3 degrees for angle C. So that changes stuff, right? This angle down here is not 91.7 anymore, apparently, and it's 12.3. So I'm going to set up the same law of sines proportion that I did before. The only difference is this time, instead of sine of 91.7, our new angle C is 12.3. So same math, different numbers, so you're going to get a different answer. We're going to multiply this diagonal together, and then we're going to divide by that. And we find out that leg C in this particular case is 2.8. So that's what happens when you have a true ambiguous case where it produces two different triangles. Yeah, it's twice the work, but it's not like it's terrible work. And the issue of finding just one triangle, what's going to happen is when you go to set up what you think is the second case of a triangle, when you get to this step right here, you're going to find out that this angle would be negative. Like there's not enough angle space to make another angle. So in that case, you wouldn't consider the second part of the ambiguous case because it doesn't make a triangle. You would just consider the first case. So, mystery solved, huh? Alright, so now I like law of cosines better. But it doesn't matter because you have to be able to do both. When you have the side, 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 or the side, angle, side setup, you have to use law of cosines if you're looking at an oblique triangle. So you might recognize that the beginning of law of cosines looks an awful lot like Pythagorean theorem. It is actually a derivation of the Pythagorean theorem with a little bit of fun thrown in there because Pythagorean theorem is specific to right triangles. So notice, because you do have to have this memorized, right? If you start off with leg A in cosines, then you have to end with angle A. Same thing with B and C. So these are one of those formulas where like they're just so repetitive that you end up memorizing them. All right, let's take a look at this first example.